chess is really hard. 100 training hours for a computer is far worse than thousands of training hours for yours truly. The objective is pretty simple, making a machine learning agent to play chess at a high level. But granted, things that are simple aren't necessarily easy, as we'll see later on. The original goal is to make something that can beat me consistently, which would put it in at least the top 10% of tournament-going US chess players. But overall, this goal shifted into playing somewhat intelligent moves some of the time. And for the labor partition, I did everything. Part 1. Intelligent planning is a terrible idea, and it sucks. The original approach, the first approach I did, was DQN-based reinforcement learning, which used some sort of chess engine reward function. But what is a DQN? It's called a deep Q network, and it's basically this machine learning architecture that uses reinforcement learning to learn something called an action value function, which is basically just taking the game state, or the game board, and an action, which would be a move, and then outputting a value. And then after that, we can simply just take a argmax that gives you just like the biggest value, just like the biggest reward. So the first approach was training versus a random agent, and it didn't learn anything. And the reason I was knowing this, it's like the rewards gained per game that stayed very high, which since it was like a high negative number, it was quite bad. And for imitation learning, I thought it learned things, but it was mistaken. And on the right here, you can see just the entire model architecture with the entire just training class. So now we have just a reward function. The thing I used is called just like this chess engine reward function, where our uses something that's very good at chess to see what the quality of the moves are using some math and also just like analysis of the board. It also here's the environment creation. I used the AlphaZero board envy. And here are the training functions: reinforcement training, where it played against itself. Well, yeah. No, it played against a random agent. And then the imitation training, where it simply just watched many, many games of chess. The results was a dumpster fire. So for the first model, the reinforcement learning, it learned nothing. But for the second model, the imitation learning, it was getting like very close to 0 total reward per game, and that's like what we want. But after I took a little look, so I was thinking, oh yes, it learned something, I'm so excited. But then I checked a look at the length of the games, and turns out by the very short game lengths, it was losing almost instantly. You're saying game lengths of 2, game lengths of 16, 17, 10, 8. And it basically was just like losing the game so quickly that, of course, it didn't have time to garner much reward. So this unacceptable performance warranted just a complete shift in our plan. And we also had we as in I, had 10 days left to complete the project, so it was a bit of a scary moment. So let's fix this dumpster fire. Part 2, chess is English and Nietzsche was right. Firstly, let's talk about something called natural language processing, not to confuse with My Little Pony, which is in natural language processing, the machine learning and linguistics subfield about understanding human language. And some tasks in are like sentiment analysis, translation, summarization, and then there's this final one, text generation. And this is the one we care about because it's sort of applicable to chess. And the model approach was, chess is really just a text generation problem. If you think of moves or words in games as sentences, you're basically just generating a bunch of moves. So let's find a data set of chess games, make a corpus body of all the text, clean the data, make some n-grams, and train a model to do text generation, which would actually probably generate series of chess moves, which would play chess. For this, I used a standard bidirectional LSTM-net, which works pretty decently on the English language in most cases. I also just made the model a little bigger because I thought it would help. Granted, it took nearly 10 hours per epoch, so 120 hours of training. So for the raw data, there's 20,000 chess games, each in a form similar like this. As you can see, just a list of moves with checks and checkmate. And these games are all from Lichess, so they're just like pretty random chess games with like pretty random people, which means a massive variance of like move quality and game quality, but it doesn't really matter as this is mostly proof of concept. So data cleaning, pre-processing, I removed all the punctuation like these plus signs indicating check or the hash signs indicating checkmate because I didn't need them. Then I generated these things called n-grams, which are basically just like sequences of words. Maybe, for example, it would be like the first 3 moves of the game is an n-gram, then the first 4 moves of that same game is another n-gram, so on and so forth. Then I removed conflicting n-grams, which are like the same up till the last word and then different. So it would be like E4, D5, and then E4, E5. Those are two conflicting ones, and we want to remove those so the AI trains better, so because it doesn't have conflicting data. Then we do this thing called tokenization, which takes all these like strings of characters, these words that we can't really train on, and converts them into numbers through like a numerical representation. And that's very helpful. And then we can process this data as just like vectors of numbers corresponding to words. And this is all the code that I used to do that. Then we train the model. We put in a saver function because I was told to do that because Andrew got mad at me when I didn't. And then we just use train, and we see all the epochs, and we have the model loss, which is this metric called categorical cross entropy, and then it's just like an error metric, and then accuracy is obviously just like its accuracy prediction. So we can see here, this is the code to make the graphs. It gets pretty low accuracy, but it clearly did learn something. So it's probably going to do better than our last try. That's basically just throwing out random moves. It's not done training yet, which is quite interesting. And what's good is the loss and error is going down and the accuracy is going up. The way we know it's not done training is because the curves haven't like completely flattened out yet. Let's look at the results. We can use this function up there where we input a seed and then just do the next like num moves. Here's 14 moves. We started with the move knight c3. And here are some of the outputs. It's playing real chess openings. Now that we can hop over to chess.com and actually just like look through some of the games that I played, like the 4 games, well, we have 3 of them here. And these are just the AI playing purely against itself with none of my input whatsoever. And you can see it's playing via just like chess.com's accuracy metrics. It's playing reasonably well, and also just like by far these moves look human and reasonable. This is just like the first example of just an opening. And the main takeaway here is that even though it's not playing just like the best move in every position, it's playing moves that like look human and are actually human openings, which is far better than the other model, which was simply looks like it was playing random moves. We can go through a second example where it's playing an exchange French defense, which is like an actually real opening yet again. Just to play some inaccuracies, here it actually blunders. I'm not entirely sure why. But then even after that blunder, it's still playing mostly good moves, only going down to an inaccuracy level of play. It's not making too many like large, massive mistakes. And then for a final example, you can see this like knight c3 beginning, and here it's playing some sort of turtle type configuration. I'm not entirely sure what it's doing, but even in that case, it still looks reasonable and reasonably human, which is kind of the goal that we were going for with this model. And these accuracy scores, although they're not the highest in the world, they're reasonably good for the opening phase. So overall, we'd like to say that this project has been quite a bit of a success. We actually have created just an artificial machine learning model that learns how to play actual chess openings, both from just like actual chess, just like lots and lots of chess games, but finally just like without any understanding of chess itself, just by simply looking at the structure of the moves and treating them as words in the English language. And I think that's really, really cool, and I think that method has a lot of promise and improvement for going forward. So for final future steps for like the future, firstly, it would be nice to compile better data, which is more data, which would be like good moves from engine versus engine games, and which would be better training data overall because it's just higher quality moves. A better model, just like a more sophisticated model, I'm looking towards Transformer GAN, which would be like transformers, which is common in natural language processing, and generative adversarial networks, which are normal for like text generation. Image generation is where they're traditionally from, and this should yield better accuracy, which would just again make the model better. I'd also have challenged Andrew Wu to sort of just like a 1v1 of sorts, where we're going to be using different models on like a same dataset to try and make just like a better chess AI. And I also in the future want to make a like ChessBot 9000 is the name, but like a robot that can takes one of these models, the one that shows the most promise, and uses it to actually play chess and just like in the real world with like a board and picking up and moving pieces. And for a final thank you, special thanks to Andrew Wu for helping me set up TensorFlow GPU for 1.15. Because without him, I would be absolutely doomed, as my model would take, instead of say like 3 hours per epoch or 10 hours of PPU, it would take 30 to 50 hours per epoch, which would make it just impossible for me to finish this project. Thank you.